All right, so I'm going to take up where I left off in today's lecture because I was basically out of time and I wanted to finish this up. I am going to stream this one, that way it'll be there on Twitch as well. I don't expect anybody to be watching it, but if they are, that's great. So I'm going to assume you've already watched or you remember what we were talking about from this morning's session. It's now early afternoon here, and I have 37 minutes before I have to start my office hours. So, at any rate, so the point here is this is an example of how Lamport clocks actually work. In this case, we have three processes. Each of the processes is sending and receiving messages. And I'm focusing on messages specifically here because this is what makes it interesting when we try to come up with a consistent clock uh, value in a distributed system. We're going to see as we move through the course, this gets more complicated because we're going to have state that isn't necessarily visible to the external observer perspective. Remember, as I was mentioning in class, part of what we're doing is flipping perspectives back and forth. I'm standing in this perspective now. I'm showing you a picture of what everything looks like when it's all when I'm standing outside and I get to see all the processes independently. So I'm sort of sitting, holding this deity role or this oracle role where I can see the whole state of the entire system. But when you're looking at it from the perspective of process, all you can see are the events that change your state. So receiving a message, sending a message is really, really the simple case here. So in process one, when I start my clock, it starts at time 1, and then I decide I'm going to send a message. Now remember, I increment my clock before I send that message. So now my clock says 2. I send this to process 2. Process 2 gets this message. The message has a 2 in it, and so I say, okay, I'm going to give that the timestamp 3. And remember, there was a little conversation at the end of the class about why I'm incrementing that. Well, now you can see this distinguishes the message, the send time of the message with the receive time of the message. And so now that message was sent at time 2, it was received at time 3. That's excellent. Now, independently, process 1 can continue to increment its clock, right? It doesn't have to, uh, this isn't lockstep. Each of these processes can continue to evolve. We're keeping this simple for the example to try and help you gain the intuition to get what's going on here. So process 2 sends a message. That message is now timestamp 4 to process 3. When process 3 receives it, the message has timestamp 4 in it. So the process says, okay, well, my clock says 1. The message that just came in said 4. I'm going to bump that 4 to a 5. And now I'm going to pick the max of 1 and 5. So it's 5. So that's why process 3 now says, I received this message at time 5. Something else happens inside of process 3. The clock ticks to 6. Now process 3 decides they need to send a message to process 1. And now we bump the clock again. That message is now sent at time 7. Now you can see even here in the picture, we see things happening. Process 2 experiences something at time 5. Now notice that the time 5 between these two is really independent. Then process 1 gets that message. The message comes in with timestamp 7. It's now time, and so we increment the time. My previous clock value was 3. The message's timer was 7. I add 1 to 7, so now it's the max of 3 and 8. So I say process 1 received that message at time 8. Now process 1 decides it's going to send a message to process 2. We have to bump the timer again, so the timestamp is now 9 for the message. The message is sent at time 9, and when it's received at process 2, we take the 9, we add 1 to it. We say the previous clock value is 5, so therefore the max of 9 and 5, or I'm sorry, 10 and 5 is 10. So now we say that process 2 received that message at time 10. And so on and so forth. life continues. So you can see that not every process experienced every timestamp, but as we look at the flow of the messages through the system, we can see that the send and the receive had different times, and this is going to help us in establishing and ordering here. But one of the reasons that I pointed out, look, there's a timestamp 3 on process 1's timeline and on process 2's timeline, and we don't know what the actual ordering was relative to the process perspective, right? So as the external observer, I can go, oh, well, obviously process 1's 3 is earlier than process 1's 3, and it's like, process 2's 3 is earlier than process 1's 3, and that's okay. But in fact, we could have moved those around and made it exactly the opposite. It wouldn't have changed the observed order of the messages and the timestamps we apply to the messages. And again, that's why we get into this idea of partial ordering. The order in which some things happen does not affect the outcome of the flow of the messages through the system. And that's going to be very powerful. It's going to be important. This is one of the reasons why we're going to be able to gain some parallelism. If we didn't want parallelism, this would be really easy. We just simply run process 1 until it sends a message. Then we switch to process 2 and it receives the message. Process 1 is suspended. That's kind of the single core, single thread model. And it simplifies reasoning. The moment that we get these independent actors, and these literally could be threads or running on the same computer but on different cores, and we don't get to control that ordering. There might be other things that are slowing things down or speeding things up. There's a fair bit of non-determinism in real world systems. All right, so observations. A Lamport clock provides us with an estimate of the number of actual events in the system. So remember, we replaced our value of the clock in process I by taking the current value, adding some numeric instance to that, and storing it. So it's just an increment. We increment the clock by some value. If that value is 1, then it turns out that C sub I is the lower bound of how many events could possibly have preceded us. I mean, it's possible we had more events than that, but we couldn't have fewer events than that. So this also gives us a consistent model because it preserves the before, happens before relationship. E1 implies E2, so E2 happens after E1, in other words. And now we have the timestamps maintain that order. And remember, that was important because that gives us our consistency model. It's not strongly consistent, though, because even if the timestamps are one of the timestamps is less than the other timestamp, it doesn't actually mean that E1 happened before E2. And if you go back and look at the picture on the previous slide, that was kind of my point when I'm pointing out that we see the same clock value along different lines. We don't actually know which one happened in which order. So there's no guarantee that that timestamp indicates anything about the ordering. Let's see, what's a good way of describing that? So timestamp 6 is earlier than timestamp 5 on the picture. And that's fine because they are not causally ordered. There's no happens before relationship. So everything's consistent. All right, this is great. It didn't give us strong consistency. So how are we going to build a strong consistency clock value? So what we're going to do is we're going to use the same technique we just used, but instead of just using a single linear value, this Lamport clock, what we're actually going to do then is we're going to have a vector of these timestamps. So now we're going to have a vector that gets sent with the message, and that vector will say, this is what the sender's view of the global timestamp state was at that time. And essentially what this means is that now this becomes an indicator. I get a message from process 1, and I have an entry in my vector for process 1, and I store the last timestamp I saw from process 1. And I do the same thing for process 2, 3, 4, 5, etc., etc. I think you can probably already see, wow, this is going to grow pretty fast if I have a lot of processes involved in the system. And you're absolutely right. We're going to talk about some techniques for dealing with this, but ignore the space issue, ignore that kind of optimization issue at this point, and that will make it easier for us to reason about this. And then we'll be able to come back and paper over that, fix that later with some more complication, but it won't change our basic analysis. So we have each entry in our vector, our timestamp vector, has one slot for each process in the system. And our entry contains our timestamp. This is what time it is for us, for this process. Our entries for the other processes in the system is the last time we heard from them, the last time we received something that said, here's a timestamp. Now, okay, that's not just getting a message directly from them, but that in fact also means I'm getting vectors. I'm getting these vectors from other processes. And if I see that one of those slots has a higher numeric value than what I have stored there, I know that something has happened already and I need to update that slot. So I'm in fact merging that in. Each time I get a message, I'm merging that in and I'm taking the max of each of those over that. And of course, then I'm still going to apply the Lamport clock rule, which is going to be to increment my own message timer. And that's going to give me a new a vector that no one else is going to have. So now you're going to see, that's where we're going to end up getting that strong consistency from, is because now every one of these events has some sort of a unique vector to it. And that's going to make it a little bit easier for us. It is going to make it possible for us to come up with strong consistency. All right, so what are the rules in a vector clock? The first rule, before we execute a state change, we have to, do the clock roll forward. This is the same exact rule. It's just now written in vectorized notation. So this is just like it was with the Lamport clock. I'm going to bump up that clock value by some number. 1 is a great number, and it's one that it is a value that we're going to like because it's easy for us to reason about, like before when I was talking about how we can add up the number of states. If it's 1, we're going to be able to make some similar conclusions even with vector clocks. Now, each time we send a message, we have to send a copy of our vector clock. Remember, I told you, don't pay attention to the fact that that means that vector could be bigger than the message you're sending. Doesn't matter for our analysis. Okay, so when the receiver receives that message, this is the formal description of what I just said. We walk through that vector, and if the vector clock slot in the message comes in with a higher value, that's what we're going to actually store instead of what we already have there. If the value is smaller than what we already have there, then that means we've seen some state change from that particular node that is later than the state change that the sender of this message had seen. That's fine. So we update the vector clock, we execute rule 1, remember? Now we're going to bump our timestamp, our clock, and now we deliver the message. So our message now has a unique vector attached to it that will allow us to distinguish the when it was sent relative to the other messages in the system. So similar picture. There is, I actually, I actually had to go and hunt this slide down because the slide deck I was using is one that the Georgia Tech presentation uses, and there was a bug in it. And I said, because literally there's a place where the clock rolls backwards. And I said, nope, that violates the monotonicity. I have to figure out what's going on here. And I found out that in fact the Georgia Tech slide looks like it was derived from another slide deck, or maybe they had common ancestry. The basic idea is the same here. So I'm using this because it really captures this basic idea. Process 1 sends a message at its time 2. So the vector it sees is 200 because it's never seen any state from the other 2 processes. Now we send a message from process 1 to process 2, and when it arrives at process 2, we replace the vector, the entry there, with the 2 because that's this process's timer. This process's clock now. And then when we send our message, we increment, process 2 increments its entry in the vector to 3, and then it sends that down to process 3. And so now the message that process 3 gets is 2, 3, and of course its clock, which is now 2 because it's bumped its counter. So same thing, this is just a generalization of what we did with the Lamport clock. We're going to keep repeating this process. So now we do some processing internally. Our state rolls from 2 to 3. Notice the other two vectors don't change because we didn't see anything new from them. And then we send a message back from process 3 to process 1. Now this is fun because process 1 gets this message, which has got the 2, 3, 4 sequence in it. And so process 1 has to take its counter, increment it by 1, and then say, but I need to update these to match the incoming message. And so now the receive time is 434, even though the send time was 234. So they are unique. We have a send time, we have a receive time. Now we send another message here. This time we bump this process's vector entry. We didn't change the other two. We don't change those. We only change ours. We send the message. The message is tagged as 534. It gets to process 2. And now we do the same thing, which is the last timestamp here is 240. Well, let's see. But 5 is greater than 2, so I put that there. 3 is less than 4. And remember, I had to add 1 anyway, so I'm going to make that 4, and then I add 1 to make it 5, because that's the application of rule 1. And the third value is 4. I saw 0 there, 0, 4. Going to take the max of that is 4. So now the timestamp, the vector timestamp is 554. And I do something else. I increment my timestamp. It's now 564. So you can see the evolution of this. It's pretty much the same as it was with the Lamport clock, except now we actually have a little bit more information. And that little bit of extra information is going to allow us to reason more about this. So okay, I have lots of notation on this page. And the reason that this notation is here is just to formalize that the vector at h versus, if the vector at h is equal to the vector of k, then that means that all of the entries are exactly the same in the vector. If the vector at h is less than the vector of k, if and only if all of the vector entries in h are less than or equal to the entries in k. Okay, so what does that mean about the things that are excluded by these two rules? I mean, I think that you can get that it's a pretty simple definition of equivalence, and it's a fairly constrained definition of less than. But what about where it's not, it doesn't follow one of those rules? Well, then in that particular case, what we have are we have rules that say that these in fact are not causally related. Something happened in these two vectors that isn't in the same order. We don't have a strict ordering here, and that's what I'm trying to capture below. So v sub h is less than v sub k. So this vector h is less than vector k if and only if vector h is less than or equal to vector k, and there is some value that is strictly less than. So all of them except one could be equal, and one could be less than, and that's fine. So that just gives us a nice strong equivalence. And notice that goes both ways. That's what's giving us our stronger ability to reason about this now, is because if either side of these two are true, then the other side is true. So the converse is true of the statements. And then we say that v sub h and v sub k are not actually causally related if v sub h is not less, if neither one of them is less than the other one. That we can't say that about either one of them. And so that's like, okay, what are we going to be able to say about it? Well, we're going to get there. But the point here is that we can't say that they're equal or less than. We just know that there is no clearly established causal relationship. So again, let's talk about this. So if I have an event that has a timestamp, then if X happens before Y, then it means the timestamp of the timestamp v sub h is strictly less than the timestamp v sub k. That's what it means to have a happens before relationship. Otherwise, we don't know. We actually don't know the order. So what's nice about this is that it means that the vector timestamps themselves and the partially ordered event sets are isomorphic. In case you're not familiar with isomorphism, I did include a link to the Wikipedia page on this in the slide, and essentially it means they have the same shape or structure, even if there are details. So isomorphism is kind of like equality, but it's actually a set property, where sometimes comparing sets is a little more difficult than strict equality kinds of definitions. You can have graphs that are isomorphic that don't actually have, they have the same shape, but they don't have exactly the same details underneath it. So the key here, we're really trying to focus on consistency. Vector clocks provide us with strong consistency guarantees. The cost here, though, and I did hand wave this away earlier, now I'm going to try and start addressing a little bit of it. Okay, so the cost is the size grows linearly as we get more participants in the distributed operation. So remember, we had one entry for each process, and we already talked about it in class. Wow, how big are these entries? What do you do when the clocks roll over? Well, you can see that this problem is going to be much worse when we have a situation where we have not just one timestamp, but n timestamps, where n is some potentially arbitrarily large number. And so what we do is we're going to need to deal with this, and I'm going to talk about that in a second. But the intermission is, okay, if you remember, one of the things that we talked about that was really cool about the Lamport clock is that we could figure out roughly how many events there were in the system. Well, we can do the same thing here. Again, if we increment the clock by 1, then we can actually reason about the number of events that are causally preceded the event we're looking at. And it's just about going through and adding up the numbers. And so you have that there. It's a little bit different than the Lamport result, because in the Lamport result, we were incrementing a single clock value. Now we're implementing an array of clock values, or a vector of clock values. And so we have to add up the values of each of the individual elements in that vector. There are optimizations of this. There's a couple of papers on it I've linked here. You can do a delta. So instead of giving you a complete list, what happens is you provide a list of the values that changed in the timestamp. So now the timestamp you're sending with the message is, here's what changed in mine. And so you're doing a comparison. You're saying, this is what changed in mine, and you're sending that along. But it's an optimization. It's something you have to do in the real world, but it's not something we have to worry about when we're trying to understand our vector clocks and the benefit of them here. There is another form. There are actually quite a few other forms. I'm only going to touch briefly on this one. This is, again, a more generalized version. So we had vector clocks last time. Now we're going to go into a matrix. And so each process now keeps a vector of its clock times, so that it tracks its scalar clock values as they increase over time. And so that value then represents this process's view of the global time, the vector clock. So now what we're doing is we're taking vectors and we're adding them to we're adding one more dimension to it. So now we get time series vectors in essence, and that's what we end up with a matrix. So a sparse matrix too at that. But So we have the view of this process's view of the evolution of the clock by grabbing all of its timestamps over time, and then we look at the vector, and it also lets us to then insert the views that other people share with us because they're sending us these matrix clock timestamps in their own messages. And now you can see why trying to compress these and be very tight about it is going to become important, because this is blowing up even more. So now we keep track of not only what we see as our history, but we get to see what other processes' history was as well. And we're going to build it into this matrix clock. So now we get an even broader view of how the state has evolved throughout the system. Maybe not the most recent state. Again, this is the internal observer versus the external observer. But each time, what we've done is we've added more information, so the internal observer has greater insight into the evolution of the clock, of how this this has evolved over time. So one of the interesting things about this is it does allow us to have a form of garbage collection. So we have this nice history, but we can actually all agree, if we get to a point where everybody's state is past a particular timestamp, then I don't need to keep track of any of the history before that point, because we all agree. In other words, this becomes a way for us to identify a point at which we all know everything that happened up to that point, and therefore we don't need to keep track of anything before that point. This becomes a compaction technique. So we have this extra state, we have this extra information, and now we have an idea of what that area of variability is, what we still, everyone might not know yet. So that's actually pretty cool. Now realize the vector clock at any given node doesn't have to agree with the vector clock at any other given node. But over time, what should happen is everybody should learn about the state of the system, and that will allow us to then agree that, okay, we got this area, this region where we're not quite sure what's happened yet, but everyone knows what happened prior to this time. So that becomes a consistency point. I was rambling about that yesterday during the office hours that I recorded and probably shouldn't have. So those are matrix clocks. Like I said, there are other models of clocks, but those are the three that we're really starting with here. We're going to be using vector clocks a lot. We're going to use Lamport clocks quite a lot. There's a common relationship. You can see we're building one model of clock up from another model of clock. So what do we talk about in the lecture today and in this supplement? We talked about what are the challenges of trying to reason about time, and it was clear that it was great questions. It was clear that this is something people struggle with, and that's expected. This is what makes distributed systems and trying to reason about distributed systems interesting and challenging. We introduced the notion of logical time and logical clocks. We talked about three models of logical clocks: scalar clocks, the Lamport clocks I spent a lot of time talking about, and then the generalization of that to the vector clock. And then if that wasn't enough generalization, then the matrix clock, and a little bit about why we use these different kinds of clocks. I've talked about partial ordering. I've talked about the strengths and limitations of each of these kinds of clocks. I mean, the scalar clock is great because the timestamps aren't actually that big. Vectors get much larger. There are going to definitely be benefits, and we're definitely going to have to understand them and use them. But it's so we get stronger guarantees from it, but we have a more expensive implementation. And then matrix clocks provide us with even more insight. And I didn't really dive in very deep to matrix clocks, but I just wanted you to know that they do actually exist. And so I'm going to wrap it up here because this way I can get this posted, and you'll be able to see this. It's fortunately a lot shorter than the networking, the completion of the networking review section was. So I'm going to wrap it up there. And if you do have questions, by all means, please bring them to class or post them on Piazza or Slap Mountain Discord. Lots of different channels, different avenues for you to raise the questions. And with that, I'll call it a wrap. Thanks very much, everybody.